Right. So I asked you to look at the proofs that there are infinitely many primes. You have any questions on that? If not, then I'll skip talking about it.
Sorry, sir. Which question, sir?
This one. I asked you to have a look at the proofs in the book. Did anyone of you have a chance to look at the proof of theorem? Should be on page, let me check. Should be on page 275. Did any?
I already read it, but I don't understand, sir.
Okay, which part do you not understand particularly?
Starting from the second line of the sentence.
Second line of the sentence. Which line? Can you spell it out?
From however none of the primes Pj divides Q for if Pj line Q, then Pj divides Q minus P1, P2, Pn. I don't understand that one.
Oh, that line. Okay. Good. Thank you, Rafael. What about the rest? No question. Okay. Oh, that's sad, but okay. Well, then okay. Let's have a look at this proof. All right. So what is the idea of the proof, right? The idea of the proof is, first of all, we want to. So let's approach this from this way. If you want to show that there are infinitely many of something, then it is very hard to show that directly, right? Because how could you show you have something infinitely many directly, right? Do you have to like spell like list them all out, but you wouldn't be able to do that because there will be infinitely many, right? So typically, if you want to show if there are infinitely many something, then you want to show that the opposite is impossible, right? So the way we do it is that, well, we show that that the idea is that first we show that the opposite of the statement is impossible, right? How? While we derive contradiction by assuming the opposite of the statement. Right? So what is the opposite of the statement? So we want to show that there are infinitely many primes. Then suppose we have finitely many primes, right? Suppose there are only finitely many primes, right? Yeah. So that means what? That means we can list them all, right? Yeah. Say let's list them all, right? Let's say from the smaller, right? From the smallest, yeah. P1, P2, up to something like Pn, right? Yeah. Any question at this point? Is it clear?
Yes, sir.
Okay, great. Thank you, Rafael. But I want to ask the rest. Any question from the rest? This is clear?
It's clear so far,
It's
sir.
clear, sir.
Okay. Now, what is the next step? So if you have finally many primes, then the idea is that the key idea is here. The idea, create a new number and show that it is prime. Right? So we create a new number and show that that new number is prime. Yeah. Why? Because if we can do that, that means we contradict our assumption, right? We contradict our assumption. Our assumption says there are only finally many primes and we can list them all, right? And by showing that we have a new number that and that new number is prime, then essentially it's the same as showing that our list is not complete. We did not actually list them all. So that's where the contradiction is, right? So that's the key idea. So what's the key idea? So what is the new number? So let Q, this is the new number. Q is the product of P1, P2 up to Pn plus 1. So P1 times P2 times up to Pn plus 1. Okay. Now here's the idea. Now we show that so hold on. We create a new number when we show that it is prime. Yeah. Now, is this the new number? It may be so, or maybe not, right? So we have two cases, right? By fundamental theorem of arithmetic. What we know is that what is the statement of fundamental theorem of arithmetic? Can anyone help me? What would be the statement of the fundamental theorem of arithmetic?
It is stated that every positive integer except the number 1 can be represented in exactly one way apart from rearrangement as a product of one or more primes.
As a product of one or more primes, right? So that means Q can be written, clearly Q is positive integer, right? So Q can be written as a product of one or more primes, right? So that means what? That means if Q is written as a product of one prime, what can we conclude?
Q can be divided by prime.
Well, if Q can be divided by prime, that means Q can be written as a product of two primes at least, right? But I'm saying, what's the case if Q is written as a product of only one prime? That means Q itself is
Prime.
Q itself is a prime. That is exactly, yes. So there is Q is prime. That is one case. Or Or what? Or Q can be written as a product of two or more primes, right? So, or Q can be written as a product of two or more primes. Correct? At this point, any question? Any question? No? No? Okay. Then what is next? So we have two cases, right? The first case, if Q is prime, then what? Then what can we conclude if Q is prime? Do we have a new number?
List
That
all
is,
the prime.
I'm sorry?
We not actually list all the prime.
Correct. So then we have a new number. We have a new number, a new prime number, which means we did not actually list all primes. So it's a contradiction because we already said we can list all of them, right? And all of them are P1 up to Pn, right? So it's a contradiction. Now what about case? The second case. Now if Q is not prime, so if Q is a product of two or more primes, then you know that then Q has a prime factor, right? Is it correct?
Yes, sir.
Yeah, okay. Q has a prime factor. Let's call it, let P be, oh, let me just write it down here, right? Q has a prime factor. Q has a prime factor. Let's call it P. Right? Now then, what do we know from here? Thus, P divides Q. Is it correct? Yes, obviously, right? Okay. Now, if P divides Q, what do we conclude from here? If P divides Q, Q is this, right? Right? So, anybody? So if P divides Q, then P must divide Q minus P1 up to Pn. Yeah. Okay, let's do it this way. Okay, I think so let me put it here, right? So P must divide okay, let's do it this way. I think the explanation will be a little bit convoluted if I do it this way. Let me repeat that again, right? So we know that Q has a prime factor. Now let's take a look at the list. Does any of P1 up to Pn divide Q? That's my next question. Does any one of P1 up to Pn divides Q?
Yes.
Really?
No, I think.
Rafael, why did you say yes?
Because I thought Q was a product of two prime numbers.
But we define Q as P1 times P2 times up to Pn and then plus 1. Does it mean?
No.
No. Okay. So, no, right? No. Because if Pj divides Q for some j in 1 up to n, then Pj divides not just Q, right? If Pj divides Q, that means Pj must divide Q minus P1 times up to Pn, right? Because Pj is one of the P1, P2, and so on to Pn, right? Yeah. Yeah. So Pj must divide 1, which is impossible, right? Yeah. So which is impossible. So none of P1 up to Pn divides Q. What does it mean? That means we have, but we know that Q has a prime factor P, right? Yeah, that means P is not among P1 up to Pn, right? So that means P is a prime not in the list. Yeah, because none of P1 up to Pn divides Q, so we have a new prime that divides Q. So P is a prime not in the list, right? And we have another contradiction. Right. Any question? No question?
No, sir.
No questions there.
Okay. If not, then it is clear. Yeah. Then let me continue with GCD. I think we talked about GCD last time. We already talked about this. I'm not going to repeat that. And before we move on to uh, to 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 computation of GCD, yeah, then let me introduce a number of concepts. We already know that for GCD we take the minimum exponent, yeah, as one way to solve it. Now there is a concept here. If we say that two integers A and B are co-prime or relatively prime, even only if their GCD is 1. So, for example, if we are asked, are 10 and 21 relatively prime? Or in other words, what does it mean for two numbers to be relatively prime? It means that those two numbers share no common factor, no common positive factor except 1. So 1 is the greatest common factor or the greatest common divisor of them. Yeah. So then let's compute GCD of 10 and 21, which is what? Can you guess? I think this should be easy. Should be 1, right? Yeah. Because, well, you could compute that, or because you know that 10 is 2 times 5, whereas 21 is 3 times 7, right? So the answer is, yeah, 10 and 21 are relatively prime. What about this? Are three numbers pairwise relatively prime? So we say if you have a collection of numbers and you say that this collection of numbers is relatively pairwise relatively prime, even only if for every pair their GCD, every pair of number in the collection, the GCD is 1. So is this pairwise relatively prime?
No.
No. Why, Matthew?
The GCD of 44 and 50 is not 1.
Correct. So yeah, because GCD of 44 and 50 is actually, well, 2, right? Which is not 1. Yeah. What about the third one? Are these relatively prime? Pairwise relatively prime?
No.
No. Why?
When pair of 21 and 56 is 7.
Correct. So because the GCD of 21 and 56 is 7, which is not 1. Correct. So the key here is to compute the GCD, right? Next, the opposite sort of the dual of GCD is LCM, or least common multiple. If for GCD you look at the common divisor and find the greatest. Now for LCM, you want to find the common multiples of both numbers and look at the smallest one. So for example, what is the LCM of this? What do you think? What is the LCM of that number? Well, you could factorize them, right? What is the factorization of this number? Is what? If you divide it by 2, then it is 2 times what? Anybody has an idea? Yeah, it will be 47 7,628, which is, of course, if you divide this again by 2, you get 4 of 2 times 23,000. And then if you divide it again by 2, you get 11,907, and this is divisible by 3, I think. Times 3969, and then this is divisible again by 3 times 1323, and this is again divisible by 3, 441. So 2 power of 3 times 3 power of 3 times 441, and then this is again divisible by 3. So this is 3 times 3, 444 times 147, which is divisible again by 3. 3 times 3, 5 times 20, no, 40, 49, right? And then this is, of course, 3, 5, 7 square. Now, what about for 32? Well, this is easily divisible by 2. In fact, this is divisible by 4. Which is 4 of 3 times 50 4 times 27, which is 4 times 2. Now the LCM of that, this is the opposite of GCD. If in the case of GCD, you'll take the minimum exponent, whereas in LCM, you take the maximum. So that means you have 4 times 3 to the power of 5. So 5 times 7 square. Yeah. Yeah, you could compute it, right? So that's LCM. Yeah, I think that's what we did. Yeah. I'll just go directly with that. I'll skip the theorem. Now, what is the relationship between GCD and LCM? Now, let's have a look. Apparently, let's just take a few examples. What is GCD of 36 and 48 is what? Anybody? Quickly, can we find an answer for this? It's a 36 is 6 square, right? So it's divisible by 6. 48 is 6 times 8. So it's divisible by 6 as well, but both of them are divisible by 12. So that means this is 12. Yeah. First time 3, and then first time 4, right? And then whereas GCD, so LCM of 36 and 48, yeah. What is that? What is the LCM?
144.
144, correct. So now let's have a look. You have 12, you have 144. Yeah. Now you have 36 and 48. if you multiply them, are they the same?
Yes.
Yes. What is the result of the multiplication?
1728.
1728. Yes. Let's have a look at the next number. You have 25 times 21 is 500. 525, right? Now, GCD of 25 and 21 is, this is easy, should be 1, right?
1.
Now, what was LCM 21?
125.
Correct, 525. See? Yeah. What about this one? 120 times 500? 60,000, right? Yeah. And then GCD of 120 and 500 is anybody? 20. Yeah, 20. What about the LCM?
3,000.
3,000. Is it true 3,000? Yeah, you check it, right? So you see the relationship is this. Yeah, then this. So that means GCD of these two numbers is the same as the LCM of these two numbers divided by, the product, not this one. Yeah, is the same as the product times 42 divided by the LCM. Now, what about this one? Well, it's easy. 36 times 48 divided by GCD of 36 and 48. Now, 36 times 48. And this is GCD of, this is actually 12. So that means, well, we saw it, right? So 3 times 48 or 4 times 36, which is 144. Yeah. Any question? No? If not, then now we arrive at the GCD using I think we talked about this Euclidean algorithm. Yeah, I think we already talked about this on Monday as well. Now what we want to, so I'll skip the proof of this. I think this is very instructive if you look at the proof, but let's have a look at not just that, yeah, but we want to show this particular part. Yeah, we want to show that if you have a GCD, yeah, then, yeah. So by the way, this is tabulation, so we could use tabulation, but rather than that, let's use. I think this one is easier to understand. We want to show that the GCD, which is 2, can be written as a linear combination of the numbers. So for example, if you know that GCD of A comma B is S, then S can be written as, say let's call it D, right? Then D can be written as A plus TB for some integer S and T. Yeah. So this is important results because then we're not using it and is in application, but there are a lot of applications of this in cryptography, for example. Yeah. So this. So for example, if GCD of 6 and 14 is 2, we know that, we could compute that, then we can write that actually 2 is actually 6 times something plus 14 times something. Similarly, if you know that GCD of 25 and 21 is 1, excuse me, then 1 can be written as 25 times something and 21 times plus 21 times something. Those some things are integers, of course. Yeah, could be negative. Yeah. Similarly, yeah, for this one. Yeah. So now this gives us, this is the theorem. This is called Bezout's theorem. It says that if you have two integers a and b, then there exists integers s and t, which may be negative. Yeah, s and t may be negative, such that GCD of a and b is equal to SA times SA plus TB. Yeah. Now then, the question is, how do you find s and t? Right? Now I'll give you an example from here. So it will be easier now to write it down like this. So what is the GCD of 25, 252 and 198? So you start with 20, the bigger number, right? This one. Can you write it down through division algorithm? So what is 252 in terms of 198? 1 times 198 plus
54.
Plus, I'm sorry,
54.
54, correct. Now next, we take this 198 and 54, right? That is our next step. So 198 is how many times 54?
3.
3 times 54 plus 30. Is it 36? Right? Anybody
Yes, sir.
follow? Is it correct? Yes.
Yes, correct.
Okay, good. So now then we take the 54 and 36. Remember that, right? 54 is, what is 36?
1.
1 plus
18.
18, correct. Again, we take 36 and 18. So 36 is, what is 18?
2.
2 times 18 plus 0.
0.
And then to finish out, actually, we take this. Yeah. Yeah, we take this actually, then 18 is 0. 18 times 0 plus whatever, right? Doesn't really matter. 1 times 0 plus 18. Yeah. So let me just erase that. Should be 1 times 0, right? Now, here, now we could start from here actually. What is the, we start from here. So the GCD of 252 and 198 is 18. Is it correct? Yeah, that is correct, right? So 2052 divided by, you divide 2052 by 18 gives us 14, whereas 198, 18 is 11. So yes. Okay. So now we want to write this 18, yeah, as a linear combination of 252 and 198. So how do we do that? We start from here, the one where 18 appears as here, the one where 18 appears as the remainder, or the line before we get 0 as a remainder, right? The line before we get 0 as a remainder. So what do we know from that? We know that 18 is actually from here is what? Is equal to what? Eighteen is equal to what according to this line? Anybody?
Uh, 54 minus 36.
Correct. Or let me just write it on the multiplier, right? So 54 minus 1 times 36. Right? That means now we have this. Now in the next step, what we look at is the 36. So this 36. Yeah, the next step. So now we replace 36 with the equal amount of through the calculation. So what do we get? So this is 54 minus 1 times, what is 36? How do you write 36 in terms of this equation?
198 minus 3 times 54.
Correct, minus 3 times 54. So what do we get? This is the same as minus 1 times 198. And then plus what? Remember, you have this. Plus how many times 54?
Plus 252.
No, we don't,
Plus 3.
no, we do not compute the end result.
Hmm?
So first combine this together. Combine this and this.
4 times 54.
Correct, 4 times 54. This is how do you do that? So do not compute them, do not simplify them yet. Right? So now the next step is looking at the 54 here. Now we have, this is minus 1 times 198 plus 4 times, what is 54? 252 minus 1 times 198, which gives us 4 times 252. And then what? Plus
Minus 5.
yes, minus 5 times
198.
So we get if we say that GCD of 252 98 is S is 252 S plus 198 T, then S is 4 and then T is minus 5. Right? Okay. Any question? If not, then let's have a look at the example from the quiz. I think we have a question on that on quiz, right? So the quiz on that is, let's see. This linear combination. So the question is, what about GCD and let's do it here, right? 45 and 103. So can you guys help me here? 103 is equal to anyone?
2 times 45
Correct. Plus
plus 13.
correct. And then what's next? What is the next line?
45 equals
Mhm.
uh, 3 times 13.
Correct. Plus
Plus 6.
yes. And then what's the next line?
13 equals 2 times 6 plus 1.
Correct. And then what's the next one?
6 equals 6 times 0 times 1 plus 6, yeah.
No. Look at 6 and 1. 6 times 1 plus 0. Try to get the smallest remainder. I think we stop here, right? So here is what we do. Here it is. So here is the last line. Yeah. The previous last line is not is maybe confusing, but let's stop when with the remainder is 0, right? So we have this. So the GCD of that is actually 6, right? Yeah. Yeah, this one. So GCD. So now let's not 6, sorry. This is wrong. What I meant is not 6, but I mean it is 1. Sorry about that. Should be this one. Yeah. Now, yeah. So should be 1. Yeah. So what's next? So let's write 1 is what? Can you guys help me?
0 plus 1.
Yes, but looking at this, looking at the line, which line do you start?
Is it 13 minus 2 times 6?
Correct. That's where we start. This one. Yeah. And then 13 minus 2 times anybody?
45 minus 3 times 13.
Correct. Minus 3 times 13. Now at this point we simplify, we collect the terms, the 13s together. So what do we have? We have minus 2 times 45. And then plus,
Plus 4 times 13.
correct, 4 times 13. Not 4 times 13. Hold on a second. Careful. Shouldn't be 4. Careful.
7.
7 times 13. Remember, this is we have 2 here. Yeah. And what's next? Which one do we replace? 45 or 13? Which number do we replace?
13.
Correct. So minus 2 times 45 plus 7 times, what is 13 then?
$103 minus 2 times 45.
2 times 45. And so, how about connecting them together? That means we have 7 times 103 and plus what? What is time 45?
Minus 16 times
Correct. So
45.
yes, minus 16. So that would be the answer to that. So the coefficient of 45 is minus 16 and coefficient of 103 is 7. Now, I think we also have a question on the 7, namely the GC, checking the GCD of this one. Let me use another space here. GCD of 6n plus 1 and 17n plus 3. So let us finish this and before we finish the class. I think this is one of the question, right? Who asked this? I think I believe one of you asked this question on the reflection. So 6n plus 1. If we only want to so the way we do it is, of course, so you start from here. So 7n plus 3 is, what is 6n plus 1 times what? Well, times 2 actually, yeah. Plus what? You still have n plus 0, right? Yeah. Do you guys follow me here? No, not n plus 0, n plus 1, sorry. Yeah. And then you take this and this. So 6n plus 1 is 6 times n plus 1 minus 5. Now this is not a good form. I would usually start instead with 5 with hold on a second. Yes. No, this is fine. 6n plus 1. Now, okay, let's see. There should be a way to solve this easier. We could argue that that minus 5 is a remainder. Okay, anyway, let me try find out the simpler form for this and discuss the answer next week. Yeah. Let me take this as something that we have to solve next week. So we still have time next week. So we'll do that for this question because we are running out of time. Right. So any questions so far? Besides this?
No, sir.
No? Okay, if there's no questions, so let me conclude the session today. I will revisit this problem next week, and we'll see, so we'll discuss it, right? And with that, let me finish and thank you. See you guys next Monday.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.